Hello, and welcome to the eTech podcast with me, your host, Ryan Morn. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. Thanks very much for joining us today from wherever you might be listening. Today's podcast is going to be all about battery degradation and a few other sort of interconnected things. And basically, this is because we had several requests from listeners who've been really interested in battery degradation and also state of health and what that means and how it works. One listener in particular, Mike, thank you very much for the question. Mike specifically wanted to know if there was anything that he could do to minimize degradation in his new electric vehicle. And as it happens, this ties in perfectly with an episode we've been planning for a while, specifically looking into these kind of things. So it's perfect. So thanks for the questions, and here's our podcast. So first of all, it's probably helpful really to understand what we mean by degradation in an electric vehicle battery, and then also the mechanisms behind this, so how it happens. As we know, EV battery packs are made up of hundreds of lithium battery cells. We did a podcast on cell technology a while back, and we'll put a link to that below in the notes. But when an EV is built, it's got a nice new shiny battery pack, and it has a certain capacity, and that the capacity to store electrical charge. But in use over time, this capacity is slowly reduced, and this is called degradation. In the electric vehicle world, it's generally considered that when a battery reaches 80% of its original capacity, it's then no good for use. So in a vehicle which has a 40 kilowatt hour battery pack as new, that would mean degradation down to 32 kilowatt hours of capacity, and then it would be considered to be no use. That's quite extreme degradation. So it's not that that's what they all do, but it's just basically when EV manufacturers talk about the battery being no good anymore, it's not that it's completely no good, it's that it's down to 80% of its original capacity. Okay, it's helpful to remember a kilowatt hour is a unit of energy of storage, and it equates to 1 kilowatt of power for a period of 1 hour. So it's always a little bit hard to get your head around this concept, I think. But basically means a 40 kilowatt hour battery will take 5.7 hours to fully charge from a 7 kilowatt charger. So just to get it again, so if you're charging up a 40 kilowatt hour battery and you're feeding charge into it at the rate of 7 kilowatts, it'll take 5.7 hours to fully fill that battery. Slightly confusingly, BMW still express their battery capacity in terms of amp hours. It's basically the same unit of measure as a kilowatt hour, except to get from amp hours to kilowatt hours, you have to multiply the amp hour value by the voltage of the battery pack, because kilowatts equals volts times amps. I think BMW prefer using the amp hour measure because actually the voltage level of the battery changes depending on its state of charge. So normally you use a sort of average mean voltage value for the pack when you're calculating the kilowatt hour value. And, it's kind of technically it is more correct to use amp hour value, but it can be a little bit confusing. And I think if people are using different measurements, then it's difficult to get your head around. But again, it's the same principle, exactly the same principle. It's the same unit of measure. It's just divided by the pack voltage. So kilowatt hours, talking about a unit of energy storage, whereas kilowatts is power. Okay, so kilowatts is power. So a motor will be 100 kilowatts power. So it's important to get those the right way around, your kilowatt hours and your kilowatts. Okay, so many EVs report a battery state of health parameter. We've had some people asking what this means, what's that all about. So basically the state of health parameter, it's calculated by the BMS comparing the actual amount of electrical charge required to move the battery from one point on its charge curve to another versus the amount it would have taken when the battery was new. So effectively, state of health is a measure of degradation of the battery. And essentially this all comes back to the fact that lithium cells, they have this S-type charge curve. So when there's not a linear relationship between the voltage of the cell and how much it's charged, as there are with some batteries. It's an S curve. So what you have to do is measure, if you're measuring the voltage of the cell, you have to know what that relates to in terms of a point on its charge-discharge profile. So there's a little bit more to it than there is with some other battery technologies. So this state of health parameter is basically saying, okay, so how degraded is my battery pack? How much is it taking me to move up the charge curve at this particular point in time? There will be things that affect that state of health parameter, which is why they change. So some people have noticed, for instance, if they rapid charge their cars, they get a different state of health measurement. So if they don't rapid charge, if it's a hot day, if it's a cold day. So, I mean, it's fair to say that it's a dynamic measurement. It's based on measurements from the pack compared to an original lookup table. So there are some inaccuracies in the measurements. So it's not like completely, totally 100%. It is more of, I would say, an indication of state of health rather than an absolute parameter. So how do we do these measurements? Well, what we're doing is we very accurately measure the current flowing in and out of the battery pack, and we use a technique called Coulomb Counting. So basically, if we know the voltage and we know the current flowing into the pack, very accurately can measure how much electrical charge is going into the pack, and then the reverse of that, when it comes out, we can measure it as well, so we know how much is coming out, and that means we can compare that to the original values of the battery pack, and we would know at a particular state of charge of the battery to get from state of charge X to state of charge Y, it should require a particular amount of current flowing for a certain amount of time. And obviously we can compare the actuals to what we think that should be. So that is how you get back to that state of health measurement of the pack. One thing to bear in mind is that the gradual the reduction in capacity over time is actually it's like one of the key design considerations with EV battery systems. There's been an absolutely massive amount of investment gone into making sure that it doesn't happen too quickly. There's several different mechanisms that cause degradation inside the cell. This can be things such as lithium plating, dendrite formation, growth in the solid electrolyte layer, and also carbon stripping and copper stripping. These mechanisms are all due to the electrochemistry inside the battery. And basically what happens is they result in the loss of active material. So as the batteries charge and discharge, you've got electrochemical reactions going on, and over time it means that there's less active material inside the battery. So the key question is what can happen to accelerate or in fact decelerate these degradation mechanisms. So in all EVs, and again we talked about this already in a past podcast, and we'll put a note to that below, we have a battery management system, and the battery management system is there to protect the battery and really make sure it can't be damaged. For example, if the BMS it detects that the battery temperature is getting too high, it will restrict the rate at which it's possible to charge the battery. And that's what's behind the Chargergate issue, as it was reported a while ago with Nissan Leafs. So basically, the BMS was saying, well, the battery pack's too hot. I'm going to derate the charge rate that I'm going to let the car accept charge at to make sure the batteries don't get too hot and get permanently damaged. Okay, so the BMS is looking at a lot of different parameters inside the battery pack, including temperature, and it's checking to make sure everything's okay, and then it will manage the acceptable rate that you can charge or discharge the battery. The other classic one that you see a lot is people who are driving Teslas really hard, and that starts to derate the car. So if the Tesla battery starts to overheat, the Tesla BMS instructs the car to reduce the amount of power it's allowed to take out of the battery. So you get a warning, and basically it reduces the amount of power that the car can deliver. So typically people going flat out on the autobahn, and then they get the warning and the car gradually slows down. And the car is doing that to protect the battery, to make sure that it's not permanently damaged. One thing to remember that's really important with the battery is when you're charging or discharging the battery, it will cause the battery to heat up. Now, obviously, it's a very low charge or discharge rate. You won't really notice that because any heat will be very quickly dissipated to the surroundings. But if you're charging or discharging it really hard, you're flowing a lot of current through the battery pack. And because of then the current flow and the internal impedance of the battery and the bus bars and the other parts of the system, you'll get a lot of ohmic heating, which is current squared times the resistance. So when the battery's hot, we really want to manage that. We want to make sure it doesn't get too hot. But essentially the mechanism that's causing it to heat is high amounts of current flowing in and out of the battery pack. So the BMS, it'll be monitoring the battery temperature, and it'll see this happening. And then in order to ensure the battery isn't damaged, it'll then slow the charge rate until the temperature is dropped to an acceptable level again. So if it's a really hot day outside, the ability to get heat out of the battery pack will be reduced. And that basically means that it'll be easier for the battery to approach the upper limit of what the BMS has been programmed to see as a sort of safe top operating temperature. So if it's a really hot day, the car's going to struggle to get heat out of the battery unless it's got a refrigerant-based cooling system. So you'll see charge rates restricted if there's really high ambient temperatures. Lots of cars now also have refrigerant cooling systems or active liquid cooling systems. And the refrigerant-based ones typically are using the vehicle's air conditioning refrigeration system to subcool the coolant. So that actually means that even on a hot day, we are using more energy to cool the battery pack, but actually we're able to cool the battery pack to a much lower temperature than we could if we didn't utilize that refrigerant system. And actually what that means is that then the ambient temperature doesn't affect the charge rate or the power rating. What will happen though is that comes at a cost of energy and a cost of a much more complex system. So we need to operate that refrigeration system to keep the battery subcooled, and that has an energy penalty. So you might see the range of the vehicle exponentially reduce if you were driving particularly hard in high ambient temperatures, and you'd also effectively see the charge time of the vehicle extended, and that's because the battery were being charged up, but you'd actually be also using energy to operate the refrigerant system to cool the battery whilst it was being charged up at a very high charge rate in a high ambient temperature. So you'd be immediately sort of bleeding energy off to operate that cooling system. So that's what happens. So, and that's why active refrigeration-based cooling is used. Plain old liquid cooling is also quite good. You are limited then in terms of how much heat you can get out in high ambient temperatures. A bit of a lower power consumption than a full-on refrigeration system. So lots of vehicles have just liquid cooling systems again. But basically, in most cases, what the BMS is doing, it's really working to ensure there's no excessive damage caused to the battery pack. It does have an operating window, though, in which it'll allow the pack to operate. So what that means is there's a temperature range in which it's basically been decided that it's safe to charge or discharge that battery pack without causing excessive damage to the pack. But what you will have is that towards the top end of that operating temperature range, you will actually see more accelerated degradation in the battery pack than if it was operating perfectly in the median position, in the average position in that temperature range. So basically, there are some steps that you can take to maximize battery life and prevent degradation. So degradation mechanisms, we already talked about, but these basically all typically happen much more readily at high temperatures. So therefore, rapid charging and really hard driving that are going to result in a hot battery pack, a raised battery pack temperature due to the high current flows, are going to cause accelerated degradation compared to if you are always basically driving your vehicle perfectly normally and you're charging it from a low power charging source. If your EV does have a subcooling system with refrigeration, then it shouldn't make all that much difference. But if it's got either a passive system on the battery, so no liquid cooling, or just a regular liquid cooled system, it will make a difference. It'll be a fairly small difference, so it's arguable if you'd actually ever really notice this in the life of the vehicle. in terms of accelerating the rate or not. But it will make a difference. What you have to bear in mind is when the manufacturers are designing these packs, there's so much R&D and effort and money gone into making sure that pack has got an acceptable life that you'd have to be like continuously hitting it really hard with fast charging and hard driving to make a significant difference to the performance of the vehicle. But I would say, if it was me, if there was an option, I would basically try and slow charge overnight when ambient temperatures are good, so you don't have to worry too much about high ambience. And you basically can take advantage of using that relatively slow charge rate rather than banging it on a hard charge, fast charge all the time during the day. One other thing as well is degradation also occurs more readily at absolute top end state of charge and bottom end state of charge. So again, keeping your pack in the sort of median state of charge is recommended. I think the impact of this is fairly small. With some of the older Nissan Leafs, they used to suggest that you didn't always keep it 100% topped up. So what they'd observe was people like continuously plugging in to charge. So like you drive the car for 2 miles, you plug it in, you top it up. You drive the car for another 2 miles, you plug it in again, you top it up. And basically what they were saying was don't do that. You don't need to do that. Use the capacity of the battery pack. It's better to have the battery pack slightly discharged than it is to have it sitting there full all the time. But again, it doesn't make a massive difference. And to be honest, I think using some of the other features like preconditioning the car, so having the car, if it's cold weather, having the car plugged in and using the preconditioning features to precondition the car to warm up the interior and the battery pack will probably have more of a benefit for you than basically trying to meticulously keep the battery at 75% state of charge level. So, it's just sort of be pragmatic, be practical. You don't need to continuously keep it topped up to 100%, but I don't really think there's much wrong with having it plugged in and using those features to basically make sure that you get the battery and the car up to temperature before you get in it. To be honest, it's one of the big benefits of EV ownership, in my opinion, is that you can precondition the car, you can warm it up without having the engine running. Normally at the push of a button or using an app on a phone or something like that, or even sometimes you can program it to do it automatically at certain times in the morning, and that gives a massive benefit to the owner. It's much more comfortable. I find I don't actually have an ice scraper in my car anymore. I can't remember the last time I scraped the ice on my car. It was a very, very long time ago, although I do sometimes scrape the ice off on my wife's car. Using those preconditionings is probably better than trying to avoid having it plugged in to not have it at maximum state of charge. One big thing, there's a lot of talk about degradation, and we certainly get asked lots of questions about it. So people are obviously really interested in what's going on there. But in general, what manufacturers are finding is that in practice, the battery system degradation is much lower than was originally predicted. So that's, I think, due to the actual kind of real-world vehicle use being easier on the battery than all of the kind of modelling and the predictions that were done before the cars were launched. Very transient, kind of stop-start driving in real-world traffic with low, fairly low acceleration rates. Cars not being fully laden with 5 passengers all the time. Low average speeds in cities, which is where EVs are tending to be more widely used. Gives a battery, gives a drivetrain the opportunity to be thermally stable, gives it opportunity to cool down. I think the relatively sort of infrequent use of fast chargers as well, because of the convenience of simply plugging in overnight, means people are not actually tending to do that. So this sort of concept of like continuously fast charging your car, people don't actually really do that. A lot of early adopters of EVs have got off-street parking, they've got access to 3 7 kilowatt charge points either for overnight or at work charging, and they're making use of that. So we're not kind of getting onto the onto fast chargers and things, and that, funnily enough, has actually created some issues in that a lot of manufacturers were thinking they were going to have a lot of batteries coming out of EVs in service, and they basically found markets and applications for those batteries, because obviously if the battery gets down to 80% capacity, it's no use in your EV because you're not, it's too much weight to carry around. You want a battery that's got full capacity, but it's still got 80% usable capacity. So that would be a good battery to use in other applications, and a lot of manufacturers have developed programs to reuse those batteries in stationary storage and things like that. But then they just essentially simply have found that they're not getting enough batteries coming out of service because the batteries are lasting much better than was ever expected. So it's a really good thing if you're a consumer of a vehicle, but it's created a sort of other issue in terms of there's a problem that was thought was going to exist where a great solution had been developed for it, that then turns out it doesn't really exist as a problem at the moment, although that might change as, if EVs move away from the early adopters who've got the off-street parking and become more widespread, and maybe you might see more fast charging of certain cars and things like that. So there's a few other myths around EV batteries connected to temperature, which I think can be explained by some of what I've mentioned already, but I'll just touch on those a little bit more. So in low temperatures, when you're driving your EV and it's cold, okay, some people say that battery has less capacity when it's cold. Okay, that's not true. Okay, so when you're driving an EV when it's cold, you get less range on the car, but the battery's still got the same capacity. But it seems obvious when you say it, but I guess missed is that you need some energy to provide heat for the occupants, and that uses energy from the battery. So you end up with less driving range, but there's still the same amount of energy in the battery. It's just you're now using some of it to heat the car and keep the occupants comfortable. Obviously, if you've got a big internal combustion engine sitting at the front, you've got a lot of waste heat all the time. So having heat is generally not a problem with an internal combustion engine, but with an EV, you're taking energy out of the battery. Sometimes in very, very low temperatures, the battery cells themselves might need to be heated. So lithium batteries don't like to be charged when they're very cold, so like freezing or below freezing temperatures. So sometimes a little bit of heat might be being put into the system to warm the lithium cells up, particularly if you're going to want to charge them at a fast rate. So that might mean it might take longer to charge the car because some of the energy going in is being used to warm up the battery system rather than just going in to charge the car. But again, it's no actual change in battery capacity. In an internal combustion engine vehicle, of course, the efficiency of that car is worse when the weather's cold. Because the engine's cold, it takes longer to get up to temperature, but the advantage is when it gets up to temperature, there's always sufficient waste heat to keep the occupants of the car warm, even on the coldest of days. So, that's a really important thing. I've heard a lot of people say about how battery capacity changes with temperature and things like that. It doesn't. Battery capacity doesn't change with temperature, just what the energy in the battery is being used for changes. The other thing is that at high ambient temperatures, energy obviously is needed to operate the air conditioning system to cool the cabin and the occupants, and then also possibly the battery, depending on the vehicle. If it's got one of the refrigerant-based battery cooling systems, again, this is going to reduce the driving range of the vehicle, but it's not a change in capacity of the battery pack. If it's a high ambient temperature, the energy is going to be used also during charging to cool the pack, and that's going to reduce the rate at which it's possible to charge the battery pack up. So you might see an extended charging time if it was a really high ambient temperature, but that's likely to just be the energy going into cooling the battery pack whilst it's being charged. It may be the BMS has throttled the charge rate if it sees the cell temperatures are getting too high. But again, it's not a problem with the pack. This BMS is doing its job. It's protecting the pack. It's making sure that everything's okay. It's a cooling system doing its job, but that does require a little bit of energy. And in this way, I think it's not much different to a normal vehicle, an ICE vehicle, where it's going to use more fuel to drive the air conditioning system on hot days. So you notice the fuel consumption changing on your internal combustion engine vehicle, but maybe just not by quite as much as you would notice a difference. I think one of the other big things as well is in some of the early EVs into the market, they had relatively small battery packs. So if you look at something like the first gen Leafs with a 24 kilowatt hour pack, really, if the heating system for the car was 2 kilowatt, that's a big percentage of the pack capacity. Is going into the heating system of the car. So remember, in terms of 40 kilowatt hours, so if you had a 2 kilowatt heater connected to that pack continuously, it's going to take you like 20 hours to fully discharge that pack. So in terms of the overall power consumption of the vehicle, it's a big percentage of the energy that's stored in the pack is going on heating and refrigeration. On newer EVs, two things have happened really. One is you've got a much bigger battery pack. So as a percentage of the battery capacity, it's a much smaller amount that's being used on heating and air conditioning. The other thing that's happened as well is those heating and air conditioning systems have been made just that bit more efficient. So they use less power. So the thermal management system is optimized, better performing cooling pumps, fans, more efficient refrigeration systems, etc. So that's a big thing. It's one of the reasons why I think using the preconditioning really helps in extreme heat and extreme cold. And the other thing I would also say is if you want to sort of achieve a more consistent battery range on your vehicle, like we don't really think about this much, but it kind of makes sense if you stand back and think about it. Let's minimize the amount of solar gain on a hot day. So windscreen blinds would help that. So getting one of those foil things to put in the windscreen to stop the car getting hot on a sunny day. Tinted glass also helps that. On a very cold day, parking the car in the garage if you've got one to keep the car at a more stable temperature overnight. Using that preconditioning so that when the car is plugged in, you're using that energy rather than energy stored in the battery. That's a much more effective way, getting the car up to temperature in the morning without having a massive negative impact on the battery range. So that's it. That's all we got time for today. Actually, that's gone on a little bit longer than I expected. So that's battery degradation. So essentially, in summary, battery degradation is much less than manufacturers were expecting it to be, and that's essentially because EVs in the real world are not being used as aggressively as the test cycles that people were sort of thinking about initially when the cars were being developed. Battery degradation is a massive topic, and a huge amount of money has gone into making sure that it's absolutely minimized. There are some things you could do to sort of improve or around the edges, avoiding fast charging on really hot days, avoiding thrashing the car around. I mean, it's all kind of common sense stuff. If you drive the car sensibly, charge it from a 3 to 7 kilowatt post whenever you can. You're gonna help the car out. You're gonna help the battery out in the longer term. So I hope you found that useful and informative. If you have any other questions or things you'd like us to answer, please feel free to pop us an email or leave us a note below asking us questions. Really hope you've enjoyed the show. Don't forget to leave us a rating or hit like depending on which platform you're listening on, and of course subscribe to our channel. We try and do a podcast about once every week. Sometimes it's a little bit more often, sometimes it's a little bit less often. We're always talking about quite techie stuff to do with electric vehicles and future transport systems and things like this. There's a lot more to come, so I hope you come back and join us again soon.